Okay, everybody, we'll get started with our next presentation. So Dr. Eileen Ernenwein studied anthropology and geography at the University of Denver and received a PhD in environmental dynamics at the University of Arkansas in 2008. She's been a professor at ETSU since 2013. Dr. Ernenwein's research focuses on near-surface geophysics, archaeological geophysics, and GIS for locating varied archaeological and geological features and understanding human spatial behavior. She has conducted geophysical surveys and archaeological investigations in South America, Africa, Europe, the Middle East, and throughout North America. Noah Hall is one of Dr. Ernenwein's research students pursuing a master's in a similar field. Noah's thesis is about the use of geophysics and UAV-based remote sensing techniques to map unmarked burials and improving our understanding of the conditions that impact the success or failure of thermal imaging to detect burials. Noah Hall received his Bachelor's of Science in Geology in 2022 from the University of Wisconsin, Eau Claire.
Eau Claire, yeah.
Eau Claire. Together, Dr. Ernenwein and Noah Hall aim to create a map that showcases how many unmarked burials are within the African American portion of Singing Spring Cemetery. And here are our next speakers.
So, hello everyone, and thanks Gabe for the introduction. My name is Noah Hall, and today Dr. Ernenwein and I are going to be talking to you about what we've been doing over in Sinking Spring. So, the way that this is going to go is generally, who we are. Gabe did a fantastic job. So, just how we got involved, a little bit of the history of the cemetery, the goals, and what we're doing. We're going to show you some preliminary results of what we found so far, and then the future plans, and then I'm going to conclude for you. So a little bit about who I am. As Gabe said, I got my bachelor's in geology. I graduated fall 2022 from University of Wisconsin, Eau Claire. I did some undergraduate research doing something similar to what we've been doing out here, where we're using geophysics, and I was actually working out in Poland, and we were doing kind of this Holocaust study, and that led me to present at a conference where I met Eileen, and she told me to come on down here and basically continue doing similar work, and I've been excited to do that ever since.
I don't need that, I don't think.
Sure, yeah.
Yeah, and so I'm Eileen Ernenwein, and thank you all for having us today. As Gabe said, I've been a professor at ETSU now since 2013, and I've actually lived in this area. Now I'm at this area, being Johnson City, Tennessee. It's the longest place I've ever lived in my life, so I've considered myself a native there, and I really love it there. I've been teaching classes like GIS, which is computer mapping and remote sensing, things like that at ETSU for a long time. My research is always looking underground for usually archaeological things. I've been so lucky I started doing it in the 90s when nobody else was doing it. And so I was one of the few people that was qualified to do it, and because of that, it's really luck. I mean, I was good at it, but there was just not very many people that had the opportunity to be trained in it, and I did. And so I got to go all over the world, and I still do, and I've been on some amazing projects. But this cemetery, so cemeteries are the most commonly requested area for somebody asking me to use ground penetrating radar, for example. That's a major thing. Like, there's cemeteries all over the place that have unmarked graves, right? So that's the #1 request that I get. And the reason being, we can see underground, but also typically you do not want to disturb the graves, so you don't have the option of digging them up. And so I will do a lot of cemeteries. I have to be honest, I don't love it when I get a request to survey a cemetery, because it's very challenging. Often the results are negative, meaning not that there's nothing there, but that it's not successful. So it depends a lot on the nature of the graves, and I'll talk about that. But when Gabe contacted me, it was a little over a year ago now, I think it was summer 2023 or so, and asked me about if I could do this project. And so we started talking about it, and I thought this is really interesting. This is not the typical cemetery maybe, it's a really interesting project. So I thought, yeah, we could do this maybe. And then I discussed it with Noah when he decided to come. And he said, yeah, great, right up his alley. So that's how we got involved. And so since then, so that was over a year ago, and then Noah started the program last fall. So he's in his 3rd semester now, and we started coming out. First time we came out, well, you're gonna get into that right now. You're gonna talk about the first survey we did, so I don't need to get into that. But yeah, so we're really excited to be here. We love coming to Abingdon and doing the work here. I've gotten to know the town a little bit. So I think I'll hand it to you now for the background. Yeah.
So a little bit about the history of the cemetery. So it was established in 1773 by the Sinking Springs Presbyterian Church, and was originally, used for the burial of members of the church and for enslaved individuals. And since then, it's kind of evolved into an African American cemetery. So some of the historical figures that have kind of been in the cemetery, we have Landon Boyd, who died in 1899. He was born in slavery as a brick mason and fought in the U.S. Civil War. So his stone was really excited to see. It's at the way top of the hill up there. So if you enter, it's up on the top of the hill on the left side. It was really great to see that stone. We also have 3 Buffalo Soldiers. So these, still learning more about, but they were all believed to be involved with the Spanish-American War. So all 3 of these stones, we walked around and we found them. So that was also really cool to see. But initially, as Dr. Ernenwein was saying, when we first started the project, the first thing we wanted to do was test the soil conditions just to see if GPR would work well here. So ground penetrating radar has success in less clay-rich soils. So clay can really inhibit the signal that GPR sends out. And we'll get back into that a little bit later. But we started up in that kind of northeastern portion of the cemetery with the Good family. And we wanted to do it there because these were known burials. So hopefully if we were seeing anything, we would have something to compare it to. And the results that came back for that were really good. And ever since then, the Good family has kind of been our test marker for everything that we've been doing. If we can see the goods, then we know that we're doing a good job. So some of the goals of what we're hoping to accomplish here is creating an entire map area of the cemetery. So we want to mark out every single burial that we can see. That's the primary goal. And some of the secondary goals that we have is testing out thermal imaging. So we've had really great success with using our thermal drone, and we actually brought that along, so maybe we can bust that out later just so you can see what the drone looks like that we've been using. But we've had really great success with it, and part of my thesis is figuring out why we've had such great success with it, so that's kind of a secondary goal. Another thing that we'd like to do is create a public-facing map, so after all is said and finished, we can compile all the data into an online map that can be accessed by anyone at any time, and then you can poke around the data and see exactly what we saw. So the first things that we did, we have the geophysics, which is going to be presented by Dr. Ernenwein, and then I'll go into the drones.
Okay. I'll do that, yeah. Okay, so geophysics. Geophysics, most people think of ground penetrating radar, and that is a method, it's a type of geophysics. There's other tools as well. But first I want to cover a bigger picture of whenever we are doing any kind of geophysics, and geophysics is under the umbrella of remote sensing. So when we're doing remote sensing, we are looking at these 4 different factors to try to determine whether we can be successful with different instruments. So the first thing is preservation. Whatever we're looking for underground, it has to be preserved in some way. If it's gone, right? So preservation is obviously something we need to think about. Maybe is there still something in the ground from whatever we're looking for? So with graves, is there anything left in the ground? But actually with graves, it's interesting because I think a lot of the graves, especially at the cemetery, may have been in like pine boxes or not really substantial coffins, although we do have some metal coffins. But the grave and the material, the body, is probably long gone. There might be, if we ever excavated it, which we wouldn't, right? But there might be some teeth or something, but I think it's mostly decomposed. But when the graves were dug, every time you dig a grave, you cut down and you cut right through the layers, the natural layers in the ground, and you bury somebody, and then you fill the hole back in. And you've completely changed that soil, and you've disrupted the layering. And so often with graves, if we can't see a coffin, we see the disruption in the stratigraphy and the different soils that are now there. So you might be thinking you can't see the graves if they're gone, but we do see the grave shaft, and then that shows us where those people were buried. So preservation, or some evidence of an activity is what we're looking for. The second thing is that we need to have contrast so that we can see, we can tell the difference between where the grave is and where is there not a grave, right? So contrast, you might have played around on your phone with digital images, and you can increase the contrast and make it, dark things darker and bright things brighter. So we need to have enough of a difference between the grave and the non-grave areas. And that is something we think about for all the different instruments, which are all sensitive to different properties. So we have to think about that. If whatever feature we're looking for doesn't have enough contrast with the surrounding soil, then we won't be able to see it. So it has to have some contrast. The third thing to consider is what we call noise and clutter. So noise comes in many forms. If we are, for example, using one of the instruments we have is very sensitive to interference from power lines, and that's noise in the data. So when you're in an urban area and you're near power lines, it's going to add noise to the data. And then there is some of that in our data from that instrument. It's still okay data, but it impacted it and it made it a little bit lower quality, right? So we have to consider all the things that might be giving us noise and in the environment that we're in. And there's lots and lots of them. So we think about that, and in thinking about just the environmental conditions on the ground, are they going to allow us to use all these different instruments we have? And then the last thing is, when we're looking for something in the ground, we want to know how big it is and how deeply it's buried. So with all of these instruments, they're all a little bit different in terms of how high resolution they are. How small can you get before you can't see it? So with the geophysical instruments, typically it depends on the instrument, but usually in the context of archaeological sites, the way I describe it is, if archaeological artifacts like a little arrowhead or a piece of pottery, we do not see those. Those are too small. But when you talk about a grave or a fire pit or the foundation of a house, a pathway, things like that, that's what we map with geophysics. And those things are big enough, right? So we need to know if whatever we're looking for is big enough. So if somebody asks me, can you find these marbles, I say I can't, for other reasons besides size. And then the other thing is the depth. So as we get deeper, it gets harder and harder to detect things. The more deeply buried, they become out of the range of the different instruments, and there's just a limitation on that. So these are all the things we have to think about. With cemeteries, it's a pretty well-known target, but I'm always asking questions before starting a project. And this is why we went out and we did some test data collection with GPR at the good graves, because we went from the known to the unknown. That was our control, right? If we can see those graves and we know they're there, that means if there's unmarked graves, we should also probably see them. So the geophysical methods are, there's a lot of different tools. Geophysics is typically used by geologists for looking for minerals and oil and gas. Okay, so these are tools that were developed for a different purpose, and then people like me have kind of adapted them to use to find archaeological things and graves. But that's where their origins are, mainly. The methods that I use, there are more than these, but these are the sensors that I have. I have a magnetometer, so we do magnetometry, and that's a blue on the left. And then we have, what I'm trying to show here is that actually if you look at almost all geophysical sensors, they're all mapping something either because of its electrical properties or its magnetic properties. So a magnetometer is measuring magnetic properties, And ground penetrating radar is mainly sensitive to the electrical properties of something. And then we have an instrument called electromagnetic induction, and that measures both. It has two different types of data. It collects magnetic susceptibility and conductivity. But it all comes down to, when I talk about contrast, it's easy to imagine the contrast we need is like a different soil, right? Like that makes sense. But actually, what we really are looking for is a different electrical property or a different magnetic property. And then we can see it with geophysics. So I will go over briefly these three sensors that we use. And the first one is magnetometry. So we're familiar with how a compass works, right? You use a compass and it points at magnetic north. So the Earth has this magnetic field, and we're really, really fortunate that we have this, because actually the Earth's magnetic field is kind of like a force field, and it blocks the solar wind, which bombards the planet. If we didn't have a magnetic field, there really wouldn't be able to be life on Earth. So magnetic field's fantastic just for our own, survival, but it's also really useful. It's useful for navigation. We use a compass, but also we can use a magnetometer to measure. What we're measuring is very, very tiny variations in Earth's magnetic field. So the field is all around us right now, but objects and soils in the ground that are more magnetic, they have a secondary magnetic field that's produced that is larger if that object has a stronger magnetic property. Okay, so we can find things that have a very tiny, tiny increase in magnetism compared to things around it, and it's really neat. The magnetometers we use are highly sensitive, and you might be imagining for a magnetic thing like a magnet, right, or something metal, and you're right. Those things are highly, highly magnetic, very strong magnetic properties. But actually the magnetometer senses things, just a different type of soil that might have a little bit more magnetic minerals in it. So it's really neat, it's really sensitive, so the magnetometer can really detect very, very subtle changes in mainly soils and different packages of sediment in the ground. The instrument right there, that's NOAA using that one is, there's a bunch of different types of magnetometers. They're all kind of doing the same thing more or less. This is called a flux gate gradiometer. It's a fun word to say. We call it the TIE Fighter because it looks like kind of like the Star Wars TIE Fighter. So what it's really great. It has two magnetometers, so it's just two of the same instrument on either side. And it allows us, we're walking back and forth. We spent many, many weeks every day out there going back and forth like mowing the lawn, right? We're walking back and forth, collecting every line of data. This sensor lets you walk once and collect two swaths of data. So that's very nice. We actually have I have one with 5, and you push it on this big cart, but it's kind of too big for the environment we were in the cemetery with trees and stuff. So this is a great instrument that is really fast and very, very valuable for a lot of archaeological sites. And actually, truth be told, it almost never works for a cemetery. but it actually is working reasonably well here compared to other cemeteries. The second instrument, and the one that maybe you've heard of and you may have seen on TV or something, is ground penetrating radar. It's really cool that people know, so GPR, people know or have heard of it, and they know it's for looking underground. Unfortunately, the way it's presented in TV is inaccurate. It often shows like CSI, and it shows on a screen like a skeleton underground. That's not possible. Absolutely, I'm sorry to disappoint you, but it's not possible to see the skeleton, right? It's too small. Those bones are too small, and they don't have enough contrast with the soil, the bone material. So we will not see that. On rare occasions, people have been able to see like a brontosaurus, right? Because it's got a huge, massive bone, right? And it can be mineralized. So anyway, ground penetrating radar is really, it's easy to say, it's easy to start with an analogy of like in the airport, how they use radar to look up at the sky and look for aircraft, right? So it's monitoring the sky for aircraft going by. And it's a slightly different type of radar, but it's doing almost the same thing, and you're just taking that type of thing and you're pointing it down and going in the ground. So the antenna there, the orange box is the radar antenna, and then Erin has the computer on, she's carrying it like you carry a baby, and she's monitoring the data there. So that is like the control unit. It's sending the signal down the cable, and it's making the antenna give those pulses of radar in the ground. And then when they go in the ground, whenever there's a change and it hits something different, a little bit of energy will bounce back. So, and then it keeps going and it bounces back. So GPR is really neat because it actually gives us like a three-dimensional data set. We can see how different things look as we get deeper and deeper in the ground. So with GPR though, you'll see that we're walking back and forth again in line. So we go out there and we set up these square grids and we lay out these tape measures, and then we just survey with each instrument back and forth, and then download data, process it later. The third instrument is electromagnetic induction. It's called EMI. This is one that most people have never heard of, but it's a really great instrument sometimes. This one, it's hard to get an analogy. This is like, well, okay, the closest thing to this is actually a metal detector. If you've ever, you know what a metal detector is. It's related in the type of technology, but the similarity stops there. But anyway, it has a transmitter that is creating an electromagnetic field. It's a low frequency electromagnetic field. It creates this field, and then that field enters the ground. Anything that's in the ground that has either magnetic or electrical properties that allows it to create a secondary magnetic field. It's called an eddy current. So it's kind of like it receives the energy and then it stirs up its own energy. And so that secondary field, the more magnetic or the more electrically conductive that thing is, the bigger the response will be. So we have a diagram here showing like the transmission, and then sort of it's a profile of a pit feature, could be like a grave, and then that secondary field is created there, and then there's a receiver at the other end of the instrument, and it measures the response and it keeps logging it as you walk along. Just like the magnetometer, you just walk along and it collects as you go. This one and the magnetometer are you have to, it was really great. Noah was in marching band, which was so helpful because when you have these instruments and they are not using a GPS unit. It's possible to hook up a GPS, but it's difficult under the tree canopy and stuff. So what we do is we set it up and it beeps every second, or like 1 beep per second, and you have to walk at the constant pace, and every time you hear a beep, you need to be at the next meter mark. And you just keep going. And so you have to be very good at walking a very steady pace in a straight line, and he already knew how to do that when he started. So that was fantastic, because it does take a long time for students to learn that usually. So that was good. I actually was also in marching band, so I got, like, when I heard that, I was very excited. So, yeah, we were at it was last summer, not this past summer, the summer before he started, and he helped me with a field school I taught for archaeologists, and everybody else that was when I first started working with him, and everybody was really struggling, and he was just cruising. It was great. Okay, so that was the 3 instruments we use. Those are on the ground geophysical sensors, and those are what I've been doing for over 20 years. I've been using those instruments. But now what Noah's going to talk about are the drones. So this is new, right? I mean, you all know, like in the last 5 or 10 years, people are playing with hobby drones and stuff. They've been amazing for research, amazing. And I have been, we keep getting new ones, and recently we got one that's a thermal drone, and we got one that does LiDAR, and Noah's gonna explain what those are. But it is changing everything, and this is the first project that I've used them on with good results, like amazing results, really. So really excited about that. The thing about it is that, so most of my students use the geophysical methods I just explained, which is a lot of work to collect it, complex to understand, a lot of work to process and interpret. And now on top of that, he just has to do a whole bunch of new stuff too. So he has a really big project to do. He's doing really great, but it's a lot to do. So, all right, so I'll let him explain the drones.
So for the drone sensors that we're using, we have multispectral, which I'll explain later. Same with LiDAR and thermal. So first off, for the multispectral, we're using the DJI Phantom 4. It's just this little guy who flies around in the sky. I love him. So the way multispectral data works is that sensor that's kind of underneath it in between those two legs, it has 6 different lenses on it. So it's taking 6 pictures at a time, and it has pictures using red, green, and blue. So kind of, in the visible area, but then you also get something called near infrared and then red edge. So it's using 2 additional sensors, and then the last one is just kind of, it's an RGB composite camera, so it just takes like a regular photo that you would expect. So what it's recording is in those, the visible spectrum and then a little bit into the infrared spectrum. Whereas something like thermal is covering the near infrared as well, but then it's also getting that far infrared. So for this one, we're using the DJI Mavic 3T, and that's what we brought along today with us that we can show off later. And that picture is just kind of what it sees in the infrared camera. So this was taken during one of our night flights, and that's just me messing with our little GPS unit. So when we're out there flying, these drones operate on a flight path that we've already set up ahead of time. So that way we can just go out there, we set it down, and then we tell it to go, and it'll fly the path and then fly right back home. So that thing that I'm holding in there, it's called our RTK. So what that does is it's a highly accurate and highly precise GPS unit. So that way the drone can keep track of where it is in the air. So then every time it takes a picture, it also records where that picture was taken, in terms of like the latitude and longitude. So then that way, when we compile all the images together, it knows exactly where those images were all taken. And then lastly, we have our LiDAR drone, which is the DJI Matrice 300. So the way LiDAR works essentially is it takes this laser and shoots it, and then it will reflect back to the sensor. So this one is, the way we had it set up to record, I believe, is recording 2 returns, which means it will record the first point that it bounces back, and then if it goes further, it will record the second point that it's going to bounce back. So that's really good for getting past like leaves and tree canopy. So if you can think about it, it might hit a leaf and then might continue through and then bounce back again. So what LiDAR is able to do is essentially record topography at a really, really fine detail. So this one, I believe, is recording 6 centimeters. Or is it 8?
It depends on the height, the flying height.
Sure.
Yeah.
So this one is recording, I'll say 6 to 8 centimeters, basically per laser that it's shooting out. And this is, so let's compare it to the Tennessee LiDAR data, which is at about 1 meter per laser dot instead. So with this kind of technology, we're able to analyze the topography on a much finer scale than using what's publicly available. And this is what's really going to help us find graves, because if you have 5 meters between where you shoot lasers and graves are only 1 to 2 meters long, then you could shoot on either side of it and miss it. But when you're using 6 centimeters, then you have a bunch of returns within a grave. So that's how we're able to see those really clearly. So right now, I just want to pause, make sure everyone's good. Does anyone have any questions about what we've presented so far? Awesome. So there's going to be another, yeah, what's up?
The drones, are they doing only the surface of the ground and there's no penetration at all with it?
Yeah, so for the most part, it's going to be all surface. The best that you'll get is with the LiDAR. So kind of like I was saying, how it has 2 returns. One return could be like, let's say, like a blade of grass, but then it's going to go through the grass and actually get to like the surface level. So you're going to have what's called like a digital surface model, which is including the trees. So something like the thermal or the multispectral, it's not going to see through leaves. So you're going to get the ground, and then you're going to get kind of like the trees. So if you had like a flat line of data, it would go like this, and then it would hit a tree, and then it would come back, and it would go like that. But with LiDAR, you're actually able to get through the leaves. So it's kind of building a better surface where that one is actually going to be truer to what the ground actually is. Does that make sense?
Find the rectangle of the grave site and the indentation.
Mm-hmm. And when we get to the LiDAR data, I'll be able to explain that a little bit more too. Yeah, it looks really good. So there's going to be another pause for questions later after Dr. Ernenwein presents the geophysical results. So thanks for hanging with us.
Yeah, so that's a really big difference. The geophysics is showing us it's actually literally putting energy into the ground, or it's looking at things underground, but the drones are not. They're only able to image what's on the surface, but actually the graves are showing us a lot of evidence of what's underground by two things: by the vegetation, well, by three things. The grass there's different types of grass, and some of it's more green. And then it's also the thermal properties. So there's a difference literally a difference in the temperature of the ground at a grave versus not at a grave. And then with LiDAR, some of the graves, many of them have a very teeny tiny depression. So it's mapping the topography at a really fine scale. So it's like a very different approach, right? We're only looking at evidence on the surface, but we have it at the cemetery, and it's you don't see it when you're walking around unless you maybe, now that I know, you might, and actually right now it's really, if you walked out there, I think you'd see some of the patches of green grass over some of the graves, but you don't, it's the neat thing about drones and aerial photos and satellite images is you get that bird's eye view that you can't get standing on the ground, right? You just don't see it. And once you see the aerial images, you'll be pretty surprised at how obvious the patterns are. So here are the results, and these are preliminary. So Noah is learning. Like I said, he has a lot to learn on top of full-time classes, and he teaches some of the labs, so we're keeping him extremely busy. If anyone in here has been in grad school, you might remember that time. So he's very busy and he has a lot to learn. He is putting these data together, and we meet once a week, try to meet at least once a week and go over new things. So this is pretty preliminary. This is the whole cemetery with the magnetometer. So it's really noisy. Remember I mentioned noise. It's extremely noisy. Around the border, there was the iron fence. So the fence is highly magnetic. It's made out of, I don't know, a lot of iron, and so it's making that pattern of where is that laser, that one? Yeah, it doesn't show on the TV, but you can see around the margins it's a black, white pattern. Those are called a dipole, and what they are is the positive and the negative side of a magnetic field. Like magnetic fields have poles, positive and negative. So within about 5 or 10 meters, or I know people think in feet, 20, 30 feet, you can't, it's so strong that you can't detect any subtle changes in the ground because all it can read is the strong magnetic field from the fence. So we have that, and then we have some other large areas that are these big black and white blobby things. And then anytime there's, the graves themselves, some of them have some reinforcement bar, some rebar in them. Also just around there might be some litter, bottle caps, things like that. Those are all highly magnetic things that cause a huge anomaly in the data and obscure other more subtle things. So it's very noisy data. And I'm not surprised at a site like this in an urban area. But when you zoom in, you do see some, and if you're lucky, in between where there's less noise, you'll start to see it. So we can zoom in a little bit, and it's still there's lots of noise. All those tiny little, large and small, little half-moon cookies, those little black and white things, those are dipolar anomalies that are from most likely a metal object. It could be anything, right? Somebody dropped a pencil that had a little bit of metal on it or something. So all those things are there, but there are some little, it's more of the just slightly darker shade of gray, and many of those are graves. I know it's hard to see, trust me. We're working on this. So the next phase is going to be pulling that out of there, interpreting it, and drawing those lines. We're going to go over different ways of doing it. One is a manual way where you go in there and you literally kind of trace the lines with the computer. Or there's ways of doing kind of an automated extraction. Some of it's with artificial intelligence, some of the newer stuff. So, but there are graves in there, and you can see them. I know you probably can't see them, but trust me, there's many of them there, but they are very hidden. Here is, so let me talk about, so what would they look like? The graves that we see in the magnetometry data they have typically been a slightly elevated magnetic field. And so what I believe is that because of every grave is a grave shaft that remember the soil's gotten mixed up, and there's something about that soil that is a little bit more magnetic, and it might be that it mixed in some more magnetic soils that were deeper, and so whatever that is, there's other potential reasons why. We don't know exactly why, but pretty much every time I do magnetometry, all you know is that there's something different there, and if it is the size, shape, and orientation of a grave in a cemetery, it's very likely a grave. So that's how we interpret it, right?
Can you point to one?
Yeah. Yeah, so it would be like, yeah, it is hard to see from here. Probably these, the ones that are light, but not these, not the ones that are jumping out at you, because those are the noise. Maybe that one right there. So it is hard to see. That's a good one right there, I think, right there. We need to have a scale on there as well to show the size of those things. For reference, that is that 40 meters wide? Is that 2 20 by 20s? Mm-hmm. Yeah, so that's a 40 by 40 meter area. And here is from the electromagnetic induction instrument, that orange one. This is the conductivity. So that instrument gives you 2 data sets. It gives you conductivity, which is a measure, you know what conductivity is? It's a measure of how well something conducts electricity. It's an approximation of that. And it also gives you magnetic susceptibility. So conductivity, again, very noisy data and not a whole lot that we can see in here. I don't know if this has been successful at all because I haven't had yet enough time to look down at it. There is, so that's noise as well. I don't see any obvious, I don't think there's any graves in this data set. So we do have some periodic noise in the corner and everything. So we will work on this and see if we can extract anything. It could be a matter of processing and increasing contrast. But really, what we're doing with this project is trying all the instruments, right, and seeing what works. So this one's not been very successful. And then this is the other one from the magnetic susceptibility. This one's better. This one's always better. Magnetic susceptibility is really great. So you might wonder, we've got a magnetometer. What's different with magnetic susceptibility? And it's weird. They're related, but a magnetometer is measuring those magnetic fields as I explained. This instrument is measuring magnetic susceptibility, and it's called an active method because remember that electromagnetic induction instrument is producing an electromagnetic field and then measuring the response. The difference with the magnetometer is a passive method. It's not generating any energy. It's only recording existing fields. So the EMI instrument does a better job often of detecting some subtle things. The other difference is that it's looking at a more shallow depth. Like there's a lot of differences between the results. The best thing about magnetic susceptibility data is that it's not measuring the positive and negative poles, and it's not measuring those big electromagnetic or those big magnetic fields, those big giant black and white blobs. We don't have that in the data, so it's really, really much nicer data. And so we're looking at a map of the whole cemetery again of magnetic susceptibility. The black means it's a stronger magnetic property, and the white is the opposite. I went wrong way. If you zoom in, we do have, now I think we need to clean up the data on the lower left, but it is pretty clear on the right that we have some grave anomalies. So let me point those out. It's very subtle, but you can see, and they're all kind of in a row like graves. So they're showing up here, and they're showing up as the white. So that means that they're showing up in that portion as a lower magnetic property than the surrounding soils. I can explain it either way. For some reason, whatever, it's different is all I can say. So the soils there are less magnetic. Now the magnetometer showed them as more magnetic. And I think it's because the magnetometer is looking deeper and this one's looking very shallow. So we have a different type of soil property, shallow and deep. And in the end of the day, I mean, we always try to explain why, but often it's like, we just know that there's a difference. And again, it's the size, shape, orientation of a grave in a cemetery. It's very likely a grave. And when we look at all of them together, you know, and 3 or 4 different types of data show that there's a grave there, that's like, I mean, you really can't argue with that. So that's kind of how we do it. And then here is some ground penetrating radar data. So GPR is different. I mentioned it's kind of a 3D method. Every line of data is actually like a profile, and I'm looking at the time. So the profile, you put them all together, and then what you can do is you can slice at different depths in the ground. So this one is 90 to 120 centimeters, so pretty deep. And again, black means that there were reflections, and white means an absence of reflections where the energy just kept going in the ground. And so this one's really great because you can see these graves here, the white there, and there's quite a lot of them. This is the same area as the other data showed them there too. So pretty neat results with all of these. Oh, another GPR slice. So I think you can see them by now. This is a little bit more deep, right? So now we're getting, I mean, really deep in the ground, but we can see them pretty well. So very good results with GPR. Usually with GPR, it's very hard to see them in the slices, and you have to look at the individual lines. So pretty great results. Okay, and I'm aware of we're getting close to the end, so I could take one question and then let Noah show the drone results, if anybody had one, or we can move on. Drones, okay, this was drones, yeah.
All right, so here we have our multispectral. So what we're using is something called the leaf chlorophyll index. Essentially what that means is just how green is the grass, or like how healthy is the vegetation. So here where we're looking at these lighter blues and these greens, that's, you know, a sign of healthiness, and then the darker blues is the inverse of that. So kind of zooming in, this is kind of the area that looked really good in this image. So the best thing to point out here, right, is you have these slightly lighter blue patches in there. So the multispectral sometimes is really good, sometimes isn't, but the really good one, well, so first we have LiDAR. So what you're seeing here is, this is called a point cloud. So this is all of those laser returns that I was talking about. So this is basically a point where every laser bounced back to the sensor. So this is building up the cemetery in 3D almost. And what you're seeing here is kind of the result of that point cloud, where those lasers are now getting deeper into the ground, and we're really getting the fine topography in here. So zooming in on one point, if you're able to see it, you have kind of smaller rectangles in here. It's a little hard to see in this image, but you have smaller rectangles in there that are basically a representation of about 10 centimeters of a drop. So if you were walking, you know, your foot would sink into the ground 10 centimeters or so in that spot. So they're also in a row, if you're able to see them. So I'm going to back up to this bigger one here. So in this one, if you're able to see a lot of these bumps, here it looks kind of bumpy. That's because every little bit here is another grave all in the same row. So the LiDAR did a really fantastic job here of bringing out a lot of the individual graves. So another great success that we had was the thermal. So with the thermal, as soon as I point one out, you'll see the rest of them. Basically, if you have a darker rectangle in here, that is a cold spot relative to what's around it. So here, every little dark purple rectangle is most likely a grave. So zooming in on that as well, yeah, every single one of these that you see in here is what we would interpret as a grave. You know, it's the right shape, they're all in a row, they all kind of have the same orientation. So those are all great indicators that what we're looking at here are all different grave anomalies. And in the thermal, you know, you're able to see quite a lot. So actually, what I did was I just put a point on every rectangle that I saw. And just by doing that, I got to a total of 469 individual burials. So One thing I want to point out about the thermal that it's kind of lacking in, so obviously everywhere you have trees, the thermal can't get through the trees. So we have big like patches of missing data where we have trees. So that's kind of where the LiDAR comes in, right? Because I said the LiDAR can get through the trees. So one thing that I went ahead and did was reprocess the LiDAR in a easier to visualize way. So this is taking four separate calculations and overlaying them all together. So in the interest of time, I'm just kind of going to skip ahead here. And this is what you're seeing is the points over this image. These are the same points that was over the thermal. So we still have all 469 of those points, but now where there's no, where those data were kind of obscured by the trees, we're able to see a lot more individual rectangles that were kind of underneath that tree canopy. So one of the things that I plan on doing in the future is coming back to this image, doing the same steps, and then trying to get a more accurate total of how many graves we have here. But even in the thermal imagery, I could see that I missed a few. There's a few rectangles that don't have points on them, and then obviously this one, there's a lot of rectangles that don't have points on them. So easily looking at probably 50 more just within this image. So that's kind of what we want to do for the future. Obviously processing the data a lot more, creating better images. I really want to sit down and finally figure out how many there are. I'm getting close, getting very close. So 469 is the working number right now, only more to go. I want to thank everybody who came out and helped us. So here from left to right, we have Tyler Langford, Sayona Turner, Aaron McDowell, Amy Collins, and then Briar Schubert. So the people we don't have pictures for, we have Kathy Shearer, Gabe Christofari, and Stephen Jones, our drone guy. So this has been a great project. I've really enjoyed working on it. I know that I'm from Minnesota and I'm from the north, so this isn't my history, but I've taken a really big interest in it, especially as a person of color, and I really appreciate the cooperation we've had from everybody, allowing us to come in and really help tell the stories here. So if anyone has any questions, we'd be happy to take them. Yeah.
Are there sources of documentary or anecdotal evidence or whatever you can kind of cross-reference these two, like the numbers, to kind of zero in on your number or test your number again?
Mm-hmm. So I've spoken with the Washington County Historical Society, and they provided me with a piece of paper that had a list of every name that they had available to them. And on that paper, there was a total of 199 individuals. I don't know how many markers are actually in the cemetery. So you have the markers in the cemetery, and then that list of individuals, which I know is more than the markers. And now we have kind of where we're at. So all of this hopefully coming together and tell you how many are actually there. Mm-hmm. Yeah.
Have you folks tapped into NASA Langley Research Center? They've been doing research in LiDAR for quite a number of years, and of course spacecraft is a much bigger version of what you're doing, but you have the smaller scale. But I would think that they would partner with you in a way if you wanted to submit a grant to them. I would think that they would easily get involved and help you try to convey their technology to this application. Have you?
Yeah, I don't know. I mean, there's a lot of different grant program opportunities, and I haven't applied to a grant from NASA. Should look there. Mostly the grant funding that I've gotten was a variety of things. NSF, the National Science Foundation, is a big one for funding various statewide organizations. Stuff like this is more about history, and so like I've gotten some funding from, in Tennessee, from Tennessee Historical Commission, and Gabe did apply. So Gabe applied for a preservation grant for the cemetery, and I think got comments back and is going to reapply. And now that we have this data, it's going to be, I think, a stronger argument to get funding for preservation. Yeah.
I'm just thinking that the NASA would get a big, PR benefit from this. Their space technology is now being used in an application?
Yeah, I mean, and I have actually worked with some of my colleagues at NASA on other grants before, doing historical stuff. So yeah, that was a grant funded by the military, and they were like a partner, and it was looking at remote sensing on military lands for wasn't graves, it was archaeological sites that they were trying to preserve. But no, you're right. I think they're
And they have research in drones too. So I mean, it looks like you have a lot of the pieces that they're working on there too.
Yeah, I think so. I mean, they've been kind of at the forefront, I think, for LiDAR especially. Yeah. Yeah.
I imagine the pattern recognition would be pretty tedious for something like this. Are they automating that at all?
Yeah, so there's a few deep learning opportunities here. Some AI have been trained to detect, the rectangles that we're looking for. They're not perfect, but sometimes they work. There's also different ways. So I'm gonna back up here a little bit if I can. Oh, wrong button. I'll explain it. So something like this. Here you're able to see a lot of those darker rectangles, and those are what we are interpreting to be graves. Something like this is done automatically, so it's not detecting them for us, but it's presenting it in a much easier, like visually it's easier to see these darker rectangles than in the earlier LiDAR photo where you're looking for kind of those bumps. So there's two different ways to kind of go about that, where you're making it easier to see them for yourself, or you're using some type of AI to detect them for you, where it's pulling it out for you instead of having to like manually go in and then say, yeah, right here, right here, right here. Yeah.
You mentioned the good family and the obelisk and stuff. Could you just show us where, on one of your images?
Oh, yeah, where that's all
I
at.
was curious if we go out there to kind of orient ourselves to.
Yeah, let's use this one since I'm here. So right here, you can kind of see it. You have this darker area here, and then obviously you have Russell Road here. This is the gate into the cemetery. So then if you were to go way up here, this is where we saw the Landon Boyd obelisk, is somewhere up in this area. And then the Good family is way up here. So they're right here. This kind of row of 4 is where the Goods are. And then this is that little plot that's up there. Yeah.
I hate to interrupt, but we'll have to cut it short. But I do have some good news. Noah and Eileen have so graciously allowed us to, if you're interested, at 7:30, 7:45-ish, to come out and see the night drone flight. So if you're interested in that, you're more than welcome to at the cemetery. I would ask that you do not park in the cemetery at all. I've talked to Walter Jenny, who's the director of the Historical Society. Either park in their parking lot, or if you could park on Valley Street and then walk over, they'll be there, and you'll be able to see the drone in action and everything. So if you're interested, around 7:30, 7:45, you're more than welcome to go over there.
Can you tell us the rest of the schedule so they understand when that's?
Yep. And then right now, we're going over to 171/173 East Main Street. It's called the Colonel James White House, and that's where we're going to be doing our house tour. So if you're interested in that, we have 2 vehicles that we can take some over. If not, if you brought your own vehicle and you want to drive over and just park on Valley Street, we much appreciate that. So, and then after that, we'll be going from the house tour back to the Martha to listen to Colleen Houston from Artworks from Cincinnati to talk about murals. So, if we could get one more round of applause.
Can I just say, so the night flight that's when we get the best thermal data, like the one you see now is at night and don't have the interference of sunlight. But please, we will be on the west side of Russell Road. We'll be over there, and that's where we launched the drone. And so come over there. Please don't go in the African American part, because we don't want any people in the cemetery. You'll show up. This is like the same thing as like night vision goggles, right? So you'll be in the data. So please come over to that side, and we can show you the drone and the remote control. You can see the imagery as we're capturing it. So if you want to come, yeah. Awesome.